Today's topic is cross products, and this has some properties in mathematical and geometrical. Also, it has some properties in physics sense also, and it will work in 3 space in R3. In R3, since it has crucial crucial property, like if you have two vectors, I will use that vector has same initial points, then sometimes we might need the area of the parallelogram. However, if you find the and by calculating these lengths 1, length 2, maybe in high school you had learned to calculate the area by multiplying the one side and by up to the height. So it will be R1, R2 sine theta. However, if you have just the coordinate version of the vector 1, vector v, v prime for convenience notation, v prime, then you might write the coordinate v1, v2, and I will use just number 3 because we will work in R3. V prime is v1 prime, v2 prime, v3 prime. Then how we can calculate the area, and the cross product will give the answer for that. Then first I will explain what is cross product. It will give the vector by expecting given 2 vector, and so let U is a vector in R3, and also let V be a vector in R3. Also vectors in R3. Then the cross product. Cross product will be denoted U times V. Is also the result is a vector. The vector defined it by U2 V3 minus U3 V2 and U3 V1 minus U1 V3 U1 V2 minus U2 V1. And it looks like hard to how we calculate it, how we memorizing it. So I have one more notation. It is that form is same to the notation of determinants of 2 by 2 matrix. U1, U3, V1, V3 minus and U1, U2, V1, V2. It is cross product, and this form comes from when we calculate the determinant x, y, z, u1, u2, u3, v1, v2, v3. When you calculate it, when we choose the first vector, then you will calculate the 2 by 2 vector, 2 by 2 matrix's determinant as the cofactor. And in the same sense, by choosing another vectors in the 3 by 3 matrix, you will get another components in the vector of cross product. So let me give an example to find cross product. U cross product V. Here U is 1, 2 minus 2, and V is 3, 0, 1. Then by using just this formula, maybe we might think it is formula, it is definition. By the definition, you can calculate the U cross product V is two, 1 minus 2, 0, comma minus 1, 1 minus subtraction minus 2, 3, and the third component is 1, 0 minus subtraction 2, 3, and so it will be 2, so minus 7, 6, minus 6. The cross product is the cross product of U and V is 2 minus 6, minus 7 minus 6. So calculating the cross product is simple, and finally by using this cross product we will get the area, and I will construct how this can give the area, the information area. I will skip the number. Firstly, I will give some relationships involving cross products and dot products. Dot products. First property is U dot product U cross product V. Here the notation U and V is a vector in R2D3. If it is equal, if you calculate U dot product U cross product V is 0, then that means the vector U and the vector U cross product V, I said the cross products will give the vector as the result, and so it is also vector, and so the meaning of dot product is 0 is the two vectors u and u cross product v are orthogonal. We say that, and also when you calculate v in a product u cross product v, it is also 0, and so v is also orthogonal to u cross product v. And the next, it is called the Lagrange identity, the formula. U dot product with square, which is called the Lagrange identity, and this identity quite important in differential manifold sense also. Sometimes you, I think, since you're a graduate student, so you might learn this identity in Lie group, Lie algebra, when you didn't learn it. Yeah, and after that you might learn. Yeah, you didn't. Okay, that's okay. It is used in with current mathematics also. I just want to say that. And the third one is it has special, equality. When you calculate cross product double, then it will give this vectors. And I will calculate only D because E is also same to D. I think I have never used this property, however, it is might be useful without my major. So the cross product has that property, and I will prove that by just elementary calculating. Firstly, I said u cross product v is 0. And let me use, I erased the notation. I will write one more. U1 U3 vector, and V is V1 V2 V3 vector. Then we can calculate U dot product U cross product. U is U1 U2 U3, and as the definition, U cross product V is U2 V3 U3 V2 U3 V1 as U1 V3 U1 V2 minus U2 V1. It's a little long, and if you calculate this, U1, that first component, and U2 product, multiply the second component, U3 multiply the third component, then you can calculate the U2, U2, U3, V1 minus U1, V3, and U3, U1, V2, U2, V1. Let me find the pair. Maybe U1, U2, V3. Where is it? U1, U2, V3. So it will be cancelled. U1, U2, V3. U1, U2, V3. And U1, U3, V2. U1, U3, V2. It will cancellated. And U1, U2, V1. Oh, wait. That is U3. U2, U3, V1, and U2, U3, V1, it will be cancelled, so it is 0. And so we can get the orthogonality, and if you calculate the for B, you can get same results. So I will skip the B. And let's calculate the C. In the statement C, we should calculate the norm of cross product. Then the norm is square sum of for each vectors. I mean, is U3 V2 square, U3 V1 minus U1 V3 square, U1 V2 minus U2 V1 square. And by calculating and by grouping for each vectors, then you might be able to get the result. I think it is just calculation, and so I will skip that. U3 V3 square. You can calculate just the vector U square V square, and you might calculate U2, U3, V3, V2, and by dividing two parts, you can calculate it. And then this is same to the norm of U, and that is norm of V. And this point is U dot product V square. This form is called the Lagrange identity, and in some bad vector space, you might get the non-equality for that equation. And many mathematicians or research that why that have not equality. Finally, some algebra. Maybe in some subjects it will be used, but I don't know in detail how this identity can be used. This quality, this quality. Oh. Maybe you mean that I forgot the formula. However, it looks like this, and the by complex number, if that was inequality, it was inequality, and however, it is a little differentiation because maybe one side was 1. I'm not remembering in detail. Maybe it. Wait, that form looks like triangle inequality. And proof D, U cross product, V cross product W, and W's coordinate is W1, W2, W3, and it might be a long, so I will skip the detailed calculation. V3. This is just by using the definition of cross product, you can calculate it. And it has geometrical meaning, so before we focus on that meaning, I will calculate this. When you use the cross product U and that vector, you will get U2 W1 V1, U2 V2 W1, U3 V3 W1, U3 W3 V1. I noted the calculation in my notes. U3 W3 V2. Hot 1 V1 W2 U1 W1 V2 W1 W1 V1. If you calculate the first vector, then U1 U2 this third component and multiply subtraction multiplying U3 and the second component as the cross product. I mean, this multiplying this, subtraction this multiplying this, and then you will get the first vector that, and by adding the components U1 W1 V1 minus U1 V1 W1, and then you will get the vector U dot product V from U dot product V, U dot product V minus, and U dot product V minus, and so it gives this term, and also U dot product W and minus U3 W3 and U1 W1, and it will give the number of the dot product U and W. And similarly, in another component, by inputting these zero components, you can calculate it. Similarly, I will write in final V3 U1 V1 W3 U2 V2 W3 U2 W2 V3, and by adding W2 V2 U2 V2 W2 U3 V W3 V3 U3 V3 W3, and if you calculate it, then it will give the fact we want to get. It is known, so it is in our base field R V W. It will give that equality. And case E is also same, because we just by calculating U cross product V first, then it will change the W and V. And there are another property without the products. We focused on the product, the relationship between the product and cross product. Now I will focus on just cross products property now. Can I turn on the air conditioner? Let me give some properties of cross product. By the definition, we can see that equality easily. U cross product V is same to minus V cross product U, because its component just, we calculate that cross product by using determinant V1, V2, V3 determinants. And then if you calculate U cross product V and V cross product U, then that means just it will change it. And in determinant sense, if you change the two lines one time, then it will give a minus sign. That means this is the calculation of that matrix. And U cross product V plus W is also as the same sense. It will be distributed as the determinant. And also right distribution row is also satisfied. And the determinant sense also, if you calculate the scalar multiplication by U cross product V vector, then by improving for each vectors, it will give same value. Because just multiplying k to one vector, it will give the k multiplied to the determinant. And it is very simple, because the component the components of the zero vector will which are all zero, and the cross product definition will multiply to the vector 0 vectors in this sense, in this property, so it will be 0. And U cross product U is also 0 because that means the determinant form will have dependent column or dependent row. So this row means that determinant is 0. However, in general, we searched the last two property with dot products. So that U cross product V cross V is not equal to U cross product V cross product W, because it was the dot product U dot product V minus U dot product W, but in this sense that was different. That gives different results in the previous theorem. So you can see the fact that is not equal. It does not satisfy the associative rule. And also, let me focus on that parallelogram. We saw the property, the third property with dot product. I say the Lagrange identity, which is the formula. And in this sense, we can calculate U dot product V as by using norm of UV like that. U square V square cosine square theta, because it is square. And we will give the theta 0 to pi, and then it by grouping norm of U square, norm of V square, and then cosine square theta, and it will be sine square theta. And we calculated U cross product with square, and so we might get in the angle 0 to pi that makes sense. And this form is that L1 multiply L2 multiply sine theta, and that means norm of U, norm of V multiply sine theta, so it will give the area. Determined by two vector. Determined by two vectors U and V. That means that parallelogram. So by using this property, we can calculate the area of a triangle is determined by two vector u and v, because by dividing 2, then you can get the area. I will write just points of triangular. P2 is -102 and P3 is equal to 0.43. Then by calculating 1/2 of the cross products, one vector P1 to P2 and P1 to P3, you might be able to calculate them. P1 to P2 is -3, -2, 2, and this vector is 1, 4, 1. And if you calculate the cross product by two vectors, then you might get 15. I will skip the calculation. It is just by multiplying and subtracting this vector and repeating that for 3 vectors, and by calculate the norm of the vector, you can calculate that. It is just calculate cross product, calculate and norm, calculating the norm, you can get the results. And also we are work in the space R3. Then we might curious for volume in R3, because if you have 3 vectors, I will draw that. If you have 3 vectors, u, v, and w, then you might curious that volume and the cross product can give the volumes, that volume also by using dot product and cross product. By using 2 products, you can get that result. Let u, v, and w be vectors in R2D3. Then we say that value u dot product v cross product w is called the scalar triple product of u, v, and w, and which will give, if you calculate the absolute value of them, then it will give the volume, and I will show that fact. In this sense, I will use the form of determinants, and in physics, the form of determinant very useful. Firstly, let's denotes that vectors calculation as a determinant form, because we said this is the cross product was the form x, y, z, v1, v2, v3, that is the component of v, w1, w2, w3, that is the component of w. And by calculating this, its vector, we get the component of the v product w's component, and the dot product will producted for each component, same component. And so by replacing that x, y, z, that was x, u2, u3, v2, that was v, v2, v3, w2, w3, minus y, v1, v3, w1, w3, and plus z, v2, v3, w2, w3. And if you calculate, it was just first component of the vector v cross product w, and the second component it was third component. So inputting u1, u2, u3, you will get the dot product between u and v cross product w. So it can be written u3 by inputting x, y, z into u1, u2, u3, v1, v2, v3, v3, w1, w2, w3. That is same to this determinant. So let me show that by giving an example. Let u be a vector having component 3, minus 2, minus 5, 3 is 1, 4, minus 4, and w be 0, 3, 2. Then the cross product vw will be a minus 12 to subtraction for 0. It is just minus 2. And the third component is 3. I will write it 20. And by calculating the dot product with u, oh, 320 minus 2 plus addition minus 5, 3. Then plus 4 minus 15, 45, 49. Then its value is 49. And by calculating the determinant, u1, u2, u3, v1, v2, v3, w1, w2, w3, then the determinant will be that 3, 2. I will choose this row for our convenience because it has 0 and 1. When we choose 3, the cofactor is 4, minus 4, 3, 2, and minus 1, minus 2, minus 5, 3, 2, plus 0, and then 8, 12, that is 60, and minus 4 plus 50, 15, then minus 1 minus 4 plus 15, then minus 11. So it will give same results, as you can see. So this form is called the scalar triple product. However, it is same the determinant by the stray vector u v w. And the next theorem means the absolute value determinants u1 v1 u2 v2 in R to d2 respectively, u1 u2 u3 v1 v2 v3 w1 w2 w3, that is same to u dot product v cross product w R to d3 is equal to the area or parallelogram is equal to the area of the parallelogram by vector u1 u2 v. It will make parallelogram, and the area is same to that respectively. It is equal to the volume determined by the stray vector u v w. I will prove it. Firstly, in two-space case, by embedding to three space, we might think that means two space is a plane, and so we might think that if when we consider the two space as a plane by adding the orthogonal vectors in three space, then I will write the vector u, vector v in R2 plane. And the cross product was orthogonal with vector u, and the cross product was also orthogonal to v. So if you embedding to R to the 3 space, then the u cross product v will give the orthogonal vector with the plane R to the 2. And if you write x, y, z component, then u1, u2, where is it? u1, u2 will be right in u1, u2, 0, in R2D3 space, in the same sense, V vector will be written V1, V2, V0. And then we can calculate the area by using that, not that, by using cross products. I mean, by calculating the components. Usually the first row is written ijk because, or I used the notation xyz. It is the, you might think it is the vectors, and u1, u2, u3, v1, v2, v3. It is just notation because the cross product can be calculated from this determinant. Since it is easy to calculate, we often use this form. Then, it was 0 because our u and v vectors in R2D2 was u1, u2, 0 in R2D3 space. So if you choose the, if you calculate the determinant, then for these two vectors it will give 0, and then when you choose k, it will give the determinant u1, u2, v2, v1, v2. And also, if you want to the area A, by calculating the norm of that vector, because we showed that the norm of u cross product v was same to u norm v norm multiplying sine theta, and so that means it is same the area, and so it means that u1, u2, v1, v2 case norm, it is the u cross product v, and it is, I think that is not good notation. It is determinants, and that absolute value product k norm, and it was just 0, 0,1 vector. So it is 1, and then I will use the determinant notation. It will be absolute value of the determinant. And in 3 space case also similar. To calculate this area, we should calculate this to calculate the volume, we will calculate the area, and by multiplying this height, we can get the volume. In that sense, we might need to use projection of W to U cross product V vector, because U cross product V was orthogonal to U and orthogonal to V. So by projecting W to the vector U cross product W, then it will give its norm will give the height H. vector in R2D3. In that sense, the height H is projection V cross product W. It is also same to choose for each two vectors. So in this graph, in this drawing, I use the U cross product V. However, to calculate easily, I will choose V cross product W. Then it will give as the projection map by calculating V cross products, these vectors norm and dot product, that two vectors. It was the definition of projection, and also the volume V was area of base multiply height. Height was H. That means the area was cross product between V and W, and was the height was H. Then it will, if two vector was all not zero, then that will not be zero, as it will be cancelled. So it gives the absolute value of cross strip per product, and that was same the determinant of U1, U2, U3, V1, V2, V3, W1, W2, W3. So that theorem makes sense. And also from these facts of the theorem, we might think if the triple product that was zero, we are not consider the absolute value. If it was zero, then that means the three vectors will not determine the, what is that? I saw the word generalized by parallelogram. This shape will not make that shape, and it will in one plane, in a plane, for the three vectors. If W vector doesn't in this plane, then it will make the parallel diagram. However, if we consider so that will give the if and only if property. I mean, U, V, and W are in same plane, in the same plane. That triple cross products will be zero. It is even only because it is in the same plane, then it do not construct this three-dimensional object by the and also its value is 0 means that has no volume, and that means it is in one plane. What time is it now? I will explain the next chapter a little, and after I explain the general vector space, introduction of general vector space. I will finish today's class because I have another schedule today. I cannot continue. We need borrow. We need borrow to submit to mentoring for mentoring. So I will remain that note. Maybe we need three picture. Let's get back to our talk. So far we consider our real value vector space, and we defined it just the addition and subtraction and zero vector and scalar multiplication. We focused on these four properties, and by searching some property from them, we constructed the vector space of our real field. And I want to generalize from this real vector space to just vector space. So firstly, sometimes some people skip this first axiom by noting the additional operation is by binary operation. That means that objects in V, for that object in V, by calculating addition in the vector space V, it is closed in vector space, in just space V now. We do not know vector space yet. And also, as the axiom, it has commutativity by the operation plus, and it has associativity. It is for just the operation for addition. I will say additive operation, because it do not need to be real standard addition operator we know. And also we defined the zero vectors. Plus 0 equals 0 plus u, 0 for all u in V. And also for it, this fifth axiom is also sometimes it is needed, it is important. V, there is an object minus U, and such that U plus minus U equals 0. And the sixth axiom is also sometimes omitted by using the scalar multiplication operation is binary function. When which is called the binary function, it is omitted sometimes, because that means it is closed by the operation scalar multiplication. In V, then KU is in V. It is just closed property. Also, when we give the scalar multiplication, we saw that the distribution row KU, KV, and conversely, as the scalar sense, it can be distributed. K and M is two scalars. And it has compatibility. It is similar to associative rule. We saw that in real vector space, and we needed for the scalar 1, it will give same vector. It doesn't change the vector u for each vector u in V. It is the axiom of vector space. So if a space or if a set V satisfied this 10 axiom, then we will say that is vector space. I will finish today's topic here, and the remaining was I will do next week. Thank you.